sort of in hand, because they overlap quite a bit. Mr. Arcee, lie down. So, the theory of AC hasn't really changed a lot. In fact, that particular generator sitting there is probably a big ground power unit, and could still be in service today. That could be in a generating building right now, and be working just fine. The basic idea of an AC, three-phase AC generator has been in play for a long, long, long time. All it has to be doing is producing 60 cycles, and whatever kilowatt output or watt output or whatever it is, as long as it's doing that, we can feed it into the grid at any voltage. It doesn't really matter what the voltage is, because if it's AC, we can step it up or down to whatever our need is. There was a very, very long, protracted political and marketing and ultimately court battle between General Electric and Thomas Edison. Thomas Edison was not a very nice guy. He was one of the few records that
he was a douche to Tesla. Though,
he was before. He was way, way worse. One of the records that Thomas Edison has that will probably never get broken is the number of workplace condition laws, child labor laws, and on and on and on that were written as a result of his practices to prevent some of the stuff he did. What he did was horrific. However, he brought electricity to every building in America.
AC.
And well, no, actually, I think Edison was
Tesla's.
He did DC, but
Tesla's
he robbed
idea.
everything that he
he wanted to go down the road of DC. However, GE had figured out fairly early on that AC was way easier to deal with, and ultimately it won out because it's way easier to deal with.
I say JP Morgan bought GE from Edison.
So GE, let's see, the longest court case in U.S. history was between Alexander Graham Bell and Thomas Edison. It was a 57-year long court case, long after both of them were dead. Edison had given the U.S. patent attorney a couple of cases of whiskey to change the date on the patent that Graham Bell had filed for the carbon disc microphone, which was used in telephones up through about the mid-70s. So as you can imagine, there was a lot of money involved in that lawsuit. That's ultimately what broke Edison, was the culmination of that lawsuit. But yeah, he wasn't a nice guy, but it kind of took that kind of a personality to, convince at least our country to put wires into every building, to build all of these generators, to build all these power stations. It's sort of contrary to the current political climb about all this renewable energy. One of the things California has been a front runner in since the early 1900s has been building hydroelectric power supplies all throughout the Sierras. If you go up to I think there's like 15 of them. If you go up to Kings River, way, way back in one of the valleys in Kings River, there's one of these power stations. They just literally took a pipe, where they went up the side of the cliff, all the way up the Sierra is about 3,000 feet tall, and they put this pipe up the side of the mountain. It's like 18 feet in diameter outside. Inside diameter is about 8 feet in diameter. They made out of concrete, and I don't know. This was built in 1911. Okay, straight up the side of the mountain, 3,000 feet. Then it goes into the water table about halfway up the side of the mountain. So all the water that comes into that pipe gets 3,000 feet of head pressure and then goes to feed the turbine generators or the turbine engines that drive the generator. I don't know, this is like way before OSHA. Way in the back of this valley, it's hard to drive there by vehicle. much less get there by, by boat, by horse, by whatever. And they carried all that equipment in there and all that material and built that pipe. I don't know how many people died climbing up the side of this mountain. It's straight vertical cliff for probably the first 900 feet. Then it starts to taper off. And
Wow.
and then back after post-World War II, 1946, they came back in. And let's see, the first one I think was 18 feet in diameter and like 10 feet inside diameter, or 8 feet inside diameter. The next one they put in, it's like 15 feet outside diameter and 12 feet inside diameter because they had much better materials, right? But again, post-World War II, still not a whole lot of, still not a whole lot of technology. No, certainly no helicopters, any of that, making all this stuff work. And that's just one. Every sort of major California river has at least one of these power stations. So Great American River, Folsom River, what's the one that runs into Folsom?
Bottom of Hoover Dam's got a bunch of them.
Bottom of Hoover Dam's got a whole bunch of them. So they were really pretty innovative about this, and they never stopped. Now as you drive around anywhere, you see all the wind turbines everywhere, as well as a whole bunch of solar fields being developed. Many of the other states have started figuring out and are going there as well. California's been a real front runner. All right, so we're going to talk about the three, although truthfully we've already talked a lot about the electrochemical, the battery. So we're not going to talk about that too much. You guys kind of already have that, so I'll breeze through that pretty quickly. The alternate technologies out there, solar is kind of primarily it. There are a few other ones like fuel cells and a few other things, but they haven't really developed to any magnitude. There is a significant amount of what we're calling renewable energy in the form of wind energy, but it's still an electromechanical generator. All we've really done is come up with a different way of producing the power source for the electromechanical generator. And that's true of all the electricity made by mankind. I've got to say, because this is going to be true, the electromechanical generator is what all of your cars use. It's what all the airplanes use. So I'm going to say 99.9% is electromechanical, with the growing increase of solar energy. So maybe solar energy is up to 1% or something. I don't know. So we really have to understand how electromechanical energy is used to make current flow before we dive too deeply into AC theory. So we're going to kind of flip back and forth a little bit. All right. So the electromagnetic generator, got a nice little drawing of one. Here's kind of a nice little bitty round power station. Okay, this is probably what's sitting in the bottom of Hoover Dam. Okay, and one of many. That's a pretty good sized little generator there, isn't it? They ran these things, particularly the ones over there on the right. They ran those by steam engines. They and all kinds of different ways of running them. But essentially, as we talked about the relationship between electromagnetism, electrostatic force, and the physical motion of the electrons, we theorized that you could use magnetic flux to move electrons, or use electron movement to create magnetic flux, and therefore motion. So this relationship that exists between magnetic flux and electron movement allows us to exchange electricity for kinetic motion. Okay, so I can take kinetic motion, like the water flowing down the river, to make electricity, or I could take electricity and use it to drive the pump to make the water flow down the river. Right? Now, in all cases, once I run a little bit of electricity through this thing, wires are going to get hot, things are going to get a little bit warm, there'll be a little bit of a loss of energy. The same is true on the mechanical side. If I've got high pressure water driving the turbine here, There's gonna be some friction on the turbine components. There's gonna be some friction in the water in the pipe, et cetera. So there's also gonna be a little bit of loss, which ultimately does translate into heat as well. So the major improvements in technology ever since, early 1900s has really been shaving off just a little bit better efficiency, making things work just a little bit better. And this is particularly true where we're having to use some type of a fossil fuel to drive the generator. Now, when we're using water coming out of the mountain or, wind energy or whatever, we're going to do our best to maximize the amount of energy, but to the point that there's a cost of production issue starts becoming a problem, right? So, they're not totally, we can do better, but it works pretty well. When we're using fossil fuels, the cost of fossil fuels is so high that we're going to try and do our best to get better and better energy out of that. In using a ground-based turbine engine, we can continue to put turbine stages on that thing because we don't care what the weight is. It doesn't have to physically move. It's bolted in place. So we can extract a significant amount of energy such that the air going in, the fuel combustion process extract a whole bunch of energy, and the temperature of the gases coming out are just slightly higher than the temperature of the gases going in. And all that combustion process energy has been converted into electricity. Okay, now if we put that on an airplane, you'd never get off the ground. Put it in a ship, the ship would never move. Okay, way, way, way too big. But I can do that on ground power units. So because of that, fossil fuel isn't out of the game altogether. But if we could use fossil fuel through a ground-based unit, extract almost all of the energy out of it into the form of electricity, and then use the electricity to drive our electric car or our electric whatever, then we get a whole, we get basically 5 times as much energy per unit of fuel. Because right now, a turbine engine on an airplane is 22% efficient, whereas in a ground-based electric power plant, that same jet fuel will get you something in the neighborhood of 98, 99% efficiency. Okay? So it makes sense to develop some of these other technologies, given that we're still burning coal, we're still burning natural gas, we're still burning heavier fuel oils to run these things. And then anywhere we can put a fan up and collect solar energy, or we should do that. Of course, you got to ask yourself. Got to think about this now. If I take and put a bunch of solar panels out there, right? They're going to collect all the sunlight,
yeah,
and they're going to cast a shadow on the ground beneath them. So does that mean the Earth is going to get cooler quicker? And it's even more convoluted when you start looking at the wind generators, right? They're spinning, and the wind's going by. They're going to slow the wind down. They're going to slow the wind down so much. Does that mean the Earth is not going to spin as fast?
The Earth doesn't spin; it's flat.
Oh.
Oh.
What was that one on the Flat Earthers Society?
Yeah.
Flat Earthers all around the globe. It's on their
Free-
website.
free
All around.
Bunch of coots.
I don't know anything much about magnets. So where do the magnets come from? I mean, is it a rock or what is it?
Where do the magnets come from?
Yeah, I mean, I don't know
Hey,
anything
create
about magnets. Are they? Do we make them or do we?
So
It's ferrous material that keeps magnetism.
anytime we take iron,
It's got iron in it.
anytime we take, I covered DC theory, right?
Yeah.
but-
Yeah, okay. So anytime I take any material whatsoever and subject it to a magnetic field, it will magnetize some.
Right.
Now, some materials, in fact, pretty much all materials other than a few, they'll demagnetize very quickly. Okay? So it turns out iron, nickel,
Keeps it longer.
cobalt,
Yeah,
a couple of things will keep their magnetism longer and longer.
Yeah.
What the magnetism is the physical force. Just like we said, electrons hate each other and they'll try to avoid each other. They're pushing away from each other, but they're attracting the protons. Also, as they move, they create a magnetic field at 90 degrees to the direction of their rotation, based upon the way they're spinning as they travel around. If I can get, well, all of the different atoms doing that have all different random orbits. So the magnetic fields that they make are all canceling each other. If I can get them to spin and orbit in the same behavior, then all those magnetic fields will line up and they'll combine, they'll be additive. And then that will create a big magnetic field. On planet Earth, we just got lucky, got really lucky. Turns out the whole inside of the planet, in fact, I think it's about 94% or something like that of planet Earth is iron. And there's this big electromagnetic radiator called the sun, sending out all kinds of electromagnetic radiation all day long for, I don't know how many, 10 billion years, trillion years, however long, way more than a Yoda years. Okay?
4.5 billion.
A lot of years, okay? And so that iron has become highly magnetized. So that's the first magnet that we came up with. We didn't come up with it, but
God came up with it. Yeah.
whoever, yeah, whatever. I'm not gonna go, that's like way above the level of this class.
Is it quite literal?
I mean, we're into altitude, but that's way above our level.
Yeah, above that.
So, but yeah, so anything can be magnetized. What's important to us is this really cool relationship between electrons moving and the magnetic fields they create.
Yeah.
And of course, the electrostatic field that we talked about in capacitors. All three of those, motion, electromagnetic, and electrostatic fields. Very, very, very useful. Now, what was Ben Franklin drinking? What were these guys as they theorize, Tesla and Maxwell and Volta and all these guys, what were they drinking? What was in the water, man? That they thought all this stuff up and figured it all out. And figured it all out without ever being able to see one of these things. Okay, and the only thing they got wrong was the polarity of the battery.
Yeah, it's pretty good.
Pretty amazing.
Yeah.
Very good.
Just profoundly amazing in my mind. So it turns out that we can make an electromagnetic generator, and we can make it to where it spins round and round and round. And we'll talk about that extensively here in a little bit. But in terms of a power source, what we call renewable energy is sort of down on the lower end here. It's still all doing the same thing. It's driving an electromagnetic generator. Okay? So early on, we used reciprocating engines or steam engines, right, which were also reciprocating. We didn't really come up with a turbine steam engine until post World War II. We had them, but they weren't very effective. So primarily, everything was the reciprocating engine by some force of some combustion process. With the steam engines that we used in the trains to drive the trains back and forth, everything east of Salt Lake, they ran on coal. Everything west of Salt Lake, they ran on wood. You guys probably didn't know that, did you? No?
Say that again?
Everything east of Salt Lake, all the trains ran on coal.
Cool.
Everything west of Salt Lake, all the trains ran on wood.
Over there.
The other thing you probably didn't know is the train only ran 30 miles. Well, let me clarify that a little bit. The engine and the firebox only ran 30 miles. The train was disconnected and a new engine and a new firebox was put on every 30 miles. The engine and the firebox would then be reloaded, new water, and the engineers would stay with it. They'd go the other 30 miles back and forth. So all they did is go back and forth 30 miles. And their specialty was that 30 miles of track. The conductor was in charge of the train, and he was the captain of the train that continued on. And they never show that in the movies, right?
No.
That's the way it was. And where the two came together is called the Golden Spike National Monument, just north of Great Salt Lake.
Did they actually hit? They lined up?
They were, and then there was a little less,
A little less?
Yeah, I got a buddy of mine that works here, I'll ask him.
Okay, cool.
Did the tracks line up when they actually, he's pretty old too, he might have been there when.
When they drove the spike in.
drove the last spike in. But and of course that makes sense. In the eastern end of the country, what they have a lot of
Coal.
Coal.
coal, right? In the western end, not so much coal, but they had a lot of wood,
Mm-hmm.
right?
Wow.
So it turns out geothermal works.
Okay.
You know, there you are living on what is it, Maui? Climb up to Haleakala and throw a bunch of water in there. It's going to get nice and hot. In fact, if you can plumb it in there and have it come back out in the form of steam, and then take that high pressure steam and feed it into a turbine engine, lots of free energy. So any place the Earth is venting out, I should qualify that, venting out in a way that is not likely to explode and blow you into kingdom come. Right? You know, there's some volcanoes you maybe don't want to be so close to. But so any place you can get some free energy, does that cause the planet to cool down quicker?
No.
Yeah, probably, but so it's not going to cool down that much quicker. Coal, again, is a finite. We only got so much fossil fuel. Now, I know there's all sorts of debate about climate and global warming and all the rest of that stuff, but you cannot deny the fact that there's only so much fossil fuel underground. We will eventually run out. That's inevitable. It's not an unlimited supply. So, given that we can do a whole bunch of other really cool stuff with coal, like make plastics and paint and all kinds of other really nifty stuff, it might be better to try and use something else other than the coal. And we don't even have to get into the argument about global warming and all the rest of that stuff. Just to say, if we could do something other than the coal, that would be good. Nuclear works like a champ, but man, those little nuclear fleas are nasty. I mean, the smallest little microscopic bit of nuclear material, and it'll kill all of us. One little bitty microscopic spot put out in there, after a few minutes or maybe an hour or so of irradiating us, we're all dead. Okay? Or soon to die. Those of us that don't die within a few years will start growing strange lumps and a third head and all that good stuff, right? So nuclear, it's a good idea. Given the number of years I've spent in institutional environments where we have a tendency to mess up a train wreck, I don't know that human beings as institutions are competent enough. I actually used to work on San Onofre nuclear generating station. And I saw a lot of boo-boos that were scary. So I think in small applications, nuclear has worked out very, very well. Military development of nuclear energy for moving for propulsion systems has been, at least in the United States, has been pretty effective. Other countries, they've had some boo-boos. But in the grand scheme of things, it's probably not a good long-term viable energy source unless we can figure out how to do it off planet and transport the energy back. Because if we do it off planet, hey, the thing wears out, what do you do with it?
I'll leave it out there.
Get your big crossbow, point that puppy at the sun. Pow! It's gone. You know, it goes into the sun and turns into everything else the sun is made out of, plasma, right? So there would be ways to make use of it. There is an entity in, I think it's England, but somewhere in Europe, that has been able to create, I always get them backwards, fission and fusion. Fission is what we do now, that's the atomic bomb. Hydrogen bomb is the fusion, and it's so far up until quite recently, all we've been able to do is make one heck of a big bang out of it. But we've never been able to create a sustained fusion reaction. Well, an entity in England has done that for a very short duration. So we may not be that far away from being able to develop a true fusion reactor. And a true fusion reactor is a very small amount of material that produces an incredible amount of heat energy. So if we could develop that, now we're talking about producing a lot less radioactive material for the same net yield. As far as the turbine engine goes, that sort of has become, if we're using fossil fuels, the turbine engine has sort of become the primary propulsion unit for for electromechanical ground-based generation. Either temporary, so for example, one of the big product lines for solar turbines down by Lindbergh is making ground power units, backup ground power units, or even on, and they're all turbine engines. They work really, really well, really efficient. The kinetic, whether it's hydroelectric dam, hydro wave pump is another one that we did. In fact, I worked on a scientific project developing the model for it to see how much energy we could establish. Essentially, if you take a big long pipe, just a big huge pipe. Okay, the ones we worked with were about 7 feet, 6 or 7 feet in diameter, and about 2,500 feet long, and obviously a big huge float. And you just set it out there, floating in the ocean with a big check valve in it. So as the wave goes by, it goes whee, and then it goes back down. Well, as it's gone up, the check valve's closed, and it gets this huge column of water moving with some inertia. Well, when it comes back down, that check valve is forced open, and the water comes spewing out the top. Well, they don't make a lot of pressure, but they make a boatload of volume. So if you then take that volume and run it through, a big paddle wheel or something, then gear reduce that up to turbines or up to generator speeds, you can make this great unit. Now, we did, the project I worked on, one was to get a sense of how it behaved in the water with various currents, but also to get a sense of what kind of weather it could withstand. And we did some pretty good modeling and found out that, heavy storms, there are places you certainly don't want to put these, like anywhere a hurricane occurs. However, anywhere a hurricane occurs, it's usually too shallow to make them useful anyways. But that ultimately is a technology that we may see coming back into use in our lifetime. Obviously, it takes a pretty significant investment to do something like that. Well, guess what? Building 100-foot long fan blades and 200-foot tall towers and putting them all the way across the ridge line in Hucumba, where even the lizards don't hang out, that's a pretty significant investment. But we're doing it now. So I think the same is true here. As fossil fuels start going up in cost, which they're going to, we agree it's a finite supply. As the supply runs out, the cost is going to go up. We know some of these other technologies are going to become advantageous. What does that mean to us? Well, some of you might actually go get a job working on building those fan blades or maintaining. There's nothing in that technology that's any different than what we use in aerospace, right? So you may get a job working in it directly, or if you're not working in it directly, you will probably find what you are working on being significantly changed by the technology. A simple example of that right now is the Boeing 787. Okay, no hydraulics, all electric. Okay, how long do you think it's going to be before they come up with a battery and electric motor that can truly drive an airplane around for a while? Okay, what I think is going to happen, it's going to be kind of interesting. I think what's going to happen is we're going to flip around in terms of technology. The reason a turbine engine works and is fuel efficient is because we attach it to a really big airplane. Okay, you put it in a small little airplane like a helicopter, they suck. They suck fuel, spit it out, and they're terrible. Okay, you got to fuel them like every 45 minutes. They're just not very good range at all. But if you put it in a really, really, really big airplane, then it's pretty fuel efficient. You can fly all the way around the planet in one of them. Okay, well, with electric technology, I think what's going to happen is it's going to go the other way. We're going to find that we can build a battery, or a bunch of batteries and some small electric motors, and put them in a fairly small little electric airplane that's good for 3 or 4 hours of flying around. But that same technology doesn't work that well in very large airplanes. And you think, well, okay, how am I going to fly one of those around? You're not going to need to be a pilot. Okay? You're going to get in and say, go home. Because we've also developed all this drone technology, right? Okay, all of this automation. So we are right on the cusp. How many of you are old enough to remember George Jetson? Okay, a few of you meet George Jetson.
Yep.
Doo-doo-doo. Okay, getting his little spaceship. Doo-doo-doo-doo. Traveler. Okay,
The Jetsons.
we're right on the cusp of that. In fact, I think Google just had their first symbolic fare-paying air ride in an automated air taxi somewhere in, I forget, somewhere, wasn't in the United States. So
Commercial.
we might be working on those things.
That'll be kinda cool.
Be way cool.
Yeah.
Guess what? You don't have to do on an electric airplane.
Fuel it.
You don't have to change hot oil. Let me tell you, getting hot oil down your armpit really sucks. Okay?
So-
Been there, done that.
So you think that we're gonna go smaller? That's what you think.
Well, given the current technology, yeah, I think that's what's gonna happen. Because you can get, right now our drones are very effective, right? Small little drones,
Yeah,
the battery and the motors.
Well, the only place I could think of where they'd keep the big technology is, say we start going to Mars, and then we start flying to Mars to people.
Well, then, yeah, but again, sort of a whole different model because you've got to hurl a whole bunch of stuff up into space. So you still got to be very large. It's probably not going to be with electric technology initially. We're still using rocket engines, okay?
yeah.
Even with SpaceX and all that cool stuff, they're still burning a whole lot of burn.
It's very inefficient.
Extremely inefficient. But for me to be able to say, I want to go from work to home, I'm going to be in a little bitty thing and it'll drive me there. And if we automate it, then I don't even need traffic controllers. Okay, it's got, what was that movie with Bruce Willis and they're driving all around?
Fifth element.
Cities are three-dimensional and
Fifth element.
Fifth Element,
Fifth
yeah.
element,
You know,
He was a
okay.
bad taxi driver though.
Yeah, he was a terrible taxi driver, but that's okay. That's what we have the automation for.
Right.
Wasn't that part of the movie? The automation kept taking over, and then he finally broke it. All right, so again, some of this seems a little far-fetched, but the truth is, it really isn't that far-fetched. We're seeing man-capable carrying drones, motorcycles, other stuff. There have been several now where they fly them around over a lake. Just because if it screws up, they could go splash instead of break their neck. But we're gonna get there. Okay. So, the electromechanical generator. We could take a wire and a magnetic field and just cut and make some electricity in my wire. Grab another magnetic field, cut, have another pulse of electricity. Grab another magnetic field, cut, have another, okay? Well, all of this cutting, it's gonna be kind of inefficient. So I might wanna put it on a spindle and cut, do something like that so that it keeps sort of repeating. Well, it turns out that if I set up my wires just right in a loop, I can actually have each set of magnetic fields cutting the wire multiple times, okay? So when we do that, when the magnetic lines of flux cut across the wire, in effect, it's like a little hydraulic pump. It pumps the electrons a little bit. And then when the next magnetic field or cluster of magnetic fields or whatever I do cut, they cause a bunch more electrons to move, okay? Well, what's going to happen in our electromagnetic generator, because we designed it to be something spinning around, what's going to happen is the output of it's going to cause the electrons to move one direction for a little while, then move the other direction for a little while. So they're going to march along this way, and then they're going to stop briefly and start marching along the other direction. Okay, then they're going to stop, turn around, and they're going to do that back and forth. Okay. The primary reason we do this is simply because it's really, really easy to make a kinetic energy device that spins. Whether it's a fan blade spinning, whether it's a paddle wheel spinning, a wagon wheel spinning, it's the whole notion of an axle and a bell crank spinning around it. Okay, whether it's a wheel or a handle or a crankshaft throw, that idea as a mechanical device is really easy to make, and it's really easy to make that in a way that will last a long, long time. Okay? So by doing that, and when we get into how that particular part of it works, you'll begin to understand it. The end result is we don't get a choice. It's got to produce AC in the armature. Now note, when I use the term armature, I'm not talking about the thing that's spinning around or the thing that's fixed. The armature, as an engineering term, means the device that the output comes from. So if it's a generator, the output is electrical movement, right? I'm looking for electricity. So it could be the stationary device or stator that the output electricity comes out of, or it could be the rotor or the rotational device that the electricity comes out of. Now there are other limitations that sort of determine this, but in any case, if I've got a magnetic field and a conductor spinning around, whether it's the magnetic field spinning around or the conductor spinning around, the part that's spinning around, or the magnetic fields are spinning around it, will produce AC. If I need DC, I need to do something to convert the AC to DC. So instead of going back and forth like this, and turning around like this, and going back and forth like this, and turning around, what it does is it goes around like this, it goes like this, and then it goes like this some more, and then like a squirrel. Okay, and stop. You guys have seen squirrels, right?
Yeah.
The entire squirrel world comes to a stop every 2 seconds. Okay. And they always look up, right? You know?
Yeah.
And then they scurry around real fast, and then 2 seconds later, the whole squirrel world comes to a stop. Okay? Well, this is going to be the same thing. So in truth, if we need DC, what it's going to make is really pulsed DC. And pulsed DC is sort of a pain in the butt. It causes some problems. So if we want to smooth it out, makes things a little bit better, we might use some things like a battery or a capacitor or some other devices to help smooth the pulsing out. But if we stop and think about it, do we really need a lot of DC?
No.
Does a toaster care which way the electrons go? How about a light bulb?
No.
It doesn't care. A light emitting diode does, but it turns out that only solid state devices and one other is the battery. Okay? The battery, because we've talked about electrochemical devices, they have to have DC. They live in the world of DC. Solid state, batteries. Everything else can be AC. So let's say I want to make this big old microwave oven, which is essentially like a super duper light bulb, producing radiation out in the form of electromagnetic radiation, but not in the visible light spectrum. Okay, that's all AC. In fact, the only reason we have any DC in there, we have a small little DC power converter to run the little bitty display screen, so our little clock timer, the little push button panel. So there will be some DC to run that. A small little power supply with a little rectifier that converts the AC to DC. All the rest of it, the little motor that spins the thing around, the beeper, all the other stuff, it's going to all be AC because it doesn't need it. The toaster. Okay? You push down, right? That's all you need. No, that's not a good toaster. No, you got to have one with a nice little digital screen and display. That looks pretty good. Yeah. I'm surprised we don't have electric napkins. You pull it out, it's got a little display on it that tells you how many times it's been used before it needs to wash. Yeah. So the other part of this thing is you're going to have a magnetic field from somewhere. So we are going to cleverly name this the field. In truth, it's a magnetic field. Now, in practice, we use electricity to make the magnetic field. We can do it with a permanent magnet, and many of you, or some of you at least, may have a magnetic generator on your motorcycle. because it's very convenient on a motorcycle to just glue a permanent magnet in the flywheel and put a couple of coils in. The problem with the permanent magnet generator or magneto is if you're producing more energy, more spin of the motor, it's going to produce more and more electricity. If you don't need that electricity, too bad, you're getting it. So you got to do something you got to use that energy for something. So the way you control the output of it is by putting a big resistive heat sink in there. And what you're not using, you use to just heat this thing up, this big heater there. So that does rob a little bit of energy. But for almost all power generation, so it's really generators or small little motorcycle generators, maybe outboard engines, your lawnmower. Okay, they all use a permanent magnet generator. But pretty much everything else, they use an electromagnetic field so that we can turn the magnetism up and down by turning the electricity or the current up and down in that electromagnet. All of them, we just call it the field. Right? So armature could be stationary or rotary. That's the output. Now, if it's a motor, what's the output of a motor? Is it a motion?
Yeah.
Okay, an electric motor, whether it's a solenoid, linear motion, okay, or a spinning motor, the output is motion. So in that case, the armature, since it's an output, has to be the part that's moving, because what you want out of it is motion. But in the case of the generator, the output is electricity. So we could either spin the magnet in the armature, or we could spin the armature in the magnet, in the field. Okay, either way, both will work. Okay. Based upon what we need, there will be some maximum efficiency at an RPM that the unit will reach. So let's look at some of the factors that would go into this. And it's all engineering. You're never going to have to calculate this. But know that the engineers have considered this. Okay? The conductivity rating of the materials you're dealing with. And particularly the conductivity rating of the materials as they get warmer because you're running current through them. Okay, so their internal resistance is going to change some. So if you aim for some design current output, 100 amps, you're going to design the size of the wires, okay, the voltage that you need out, okay? So you're going to design the length of the wires and the amount of cutting that goes on, the number of different cutting exchanges that go on. You're going to design around that. That's going to be a factor. Another factor that's going to go into this is what's the length of the lever arm from the center of rotation? Is it way out here and it's spinning really slow? Or it's way in here and it's spinning really fast? Okay. Obviously, the rate of cutting, the faster I cut, the more I cut, the more electron pumps I'm going to get per unit of time, right? And isn't force moving a distance over a unit of time the components of power?
Mm-hmm.
Okay. So obviously, there'll be some RPM where this thing is really efficient. If I ask for more current out of it, it'll start getting hotter, causing the resistance to make it less efficient. If I start going faster, the rate of cutting, and I won't get too deep into it, will start creating what's called counter-motive magnetic force and interfere with your original production. So I'm throwing some of these out there and you don't necessarily have to make notes. There'll be some design parameters that the engineers will include across the board to make sure that this thing is most efficient at the design input you've got, RPM, etc. Now the problem is if I'm going to bolt this to an engine and that engine has to vary its speed because sometimes you're stopped, sometimes you're going fast, sometimes the bad guys are shooting at you and you're going really fast, okay? Then you can't keep the RPM fixed. So all you can do is design it for some average in the middle, right? So about there, and hope it works. It turns out that if I don't need to convert it to DC, I can leave it as AC. It turns out that the lower the RPM, the more efficient it is to transmit the energy. Okay, the lower the RPM it is, the easier it is to transmit the energy. Now, I haven't dove into inductive reactance. We will in a few slides, but in essence, as I build up a magnetic field, or I let the magnetic field collapse, remember we talked about hysteresis? It causes an inherent delay of that magnetic field as it's building up. So if I take my coil and I start building up a magnetic field, as that magnetic field is building up, it's cutting across all the wires of the coil, right? So as it's cutting across all the wires of the coil, it's cutting in a direction that creates a counter voltage or counter electromotive force that counters the original onset of current. The reverse, when I try to make the current smaller, let's say I shut the current off, what happens to the magnetic field? It collapses. As it collapses, what does it cut across? The coil, trying to drive the coil into keeping the same amount of current going. So anytime I have this inductive behavior going on, which is what I've got, a bunch of coils with wires cutting and magnetic fields cutting, it's going to try and naturally interfere with all of that changing current. So the slower I can go, the better, the more efficient it's going to be, because the lower that reaction is going to be, right? But here's the problem, though. We're going along really slow. Stop, all the lights go out. Okay, lights come back on, start going faster and faster, the lights are getting brighter, the lights are getting brighter, the lights are maximum bright, going along real slow, maximum, they're getting dimmer, they're getting dimmer, they're getting dimmer, they're dimmer. Oh, the lights go out. Okay, how many times would I have to do that before you guys start getting nauseous? Right? If I, made it a cycle of like the lights go out 4 times a minute. Bright, dim, out, or out, dim, bright, dim, out, back and forth. Man, you just been going, ugh, do something, light a candle, turn this thing off, right? Okay, so, well, it turns out that if you go a little bit faster, in fact, if you go a little bit faster, and a little bit faster, and a little bit faster, and once we get to the point that the lights are going out, maybe, I don't know, 15, 20 times a second, okay, somewhere in there, let's say 20 times a second, but at about 10 full cycles. So a cycle is, I go this way, stop, turn around, go this way, go all the way back, stop. I get the lights go out twice, but a full cycle of the electrons going back and forth. So if I do 10 cycles per second, that means the light went out 20 times. About half of the population stopped seeing it. You might feel just a little bit of a flicker. When I get to about 15 or 20 cycles per second, meaning they're turning off at 30 to 40 times a second, most of the human population cannot see it at all. Okay? However, it turns out that when I get to about 45 cycles per second, there's still some percentage of the population, and oddly it's women more than men, but they've plotted this out quite well. They are still subject to physiological problems, primarily in the form of migraine headaches, but other neurological issues as well. There are some people that even at 40 cycles a second can trigger an epileptic seizure, and that one actually tends to be a little bit more males. But and that's anything from about 5 cycles per second up to about 40. So we went for 60 in the great old United States and ultimately North America because they had to follow us. The rest of the world went, hey, what are those guys doing over there, man? Hey, that their electricity stuff's kind of nice. We're going to borrow some of what they got or buy it or steal it or whatever they did. However, they went at 50 cycles per second. Some of you may have traveled internationally and noticed that you do get a headache more often, or other elements, other physiological conditions from operating at 50 cycles per second. At 60 cycles per second, pretty much nobody is affected by it too much. That means the lights are going out 120 times per second. Now, it would be better if we could go 5 cycles per second, or 6 cycles per second. Well, it turns out it's actually nice to make it some division of 3, either 3 or 6, because we're going to have 3 separate generators all wound together into one, and that'll reduce some of the pulsing and some of the problems that we get with electricity, with these little pumps. But in the world of airplanes, we said, I can make this really big engine with one piston going, or I can make it much smaller with a whole bunch of little bitty pistons, 12 cylinders, Jaguar smooth, and a lot lighter, and still produce the same amount of power. Well, what they said here was, if we just spin it faster, each time I get a cutting of electrons and wire, I pump the same amount of electrons, right? So if I spin faster, I'm going to get more cuttings per unit of time. So I can just make my wires smaller, make everything smaller. I can make this thing a whole lot lighter. Okay? But now, because of all this inductive stuff we talked about, it's not going to be very efficient. Well, we don't care, because an airplane, how long is the wire in an airplane? Okay, big major power wires. A 747, you might get several hundred feet, but beyond that, that's nothing like from here all the way to San Onofre, or here all the way to Yuma, or wherever the nearest power plant is. Okay, very, very short distances. So they figured out if we go a little bit faster, we can make our power generation systems, as well, in fact, the entire system on board, the entire AC system on board the airplane, quite a bit lighter. And yeah, there's a little bit of efficiency loss, but it's hooked up to a turbine engine. Who cares? We've gained so much by making it lighter that we've more than recovered the cost in terms of fuel, right? Of that inefficiency. So 60 cycles per second and everywhere else North America, everywhere in North America, over North America or anywhere else on an airliner, 400 cycles per second. The rest of the world, 50 cycles per second. Okay, and then we use the term hertz to represent cycles per second. Okay. So yeah, 60 cycles, ground power, aircraft, 400 cycles, saves a bunch of weight, way less copper, a little bit of line loss, but again, we don't really care. The other thing that's going to be really important to this, and I don't know that I'd say this in a note.
Can you talk about line loss?
The other, and sort of simple concept. What happens to a filament in a light bulb when I run a bunch of current through it?
It's hot.
Heats up.
It's really hot and it starts emitting a whole bunch of heat, right? And it starts losing energy, not only in the form of heat, but as well as photons and a bunch of other stuff. So the more current I run through this wire, the hotter it gets. So if I can transmit my energy over long distances at a very low current value, it's not going to get very hot, is it? Okay, so how do I transmit a lot of energy at a very low current value? Jack the voltage way up. Ohm's law, right? Voltage, if current goes down, voltage goes up for a given fixed resistance. So if I bring the voltage up to 100,000 volts, I can send it a long way. Now you're going to get some line loss in the form, because high voltage, remember we said in the capacitor, it's going to create a big static field. But the big static field is going to be a lot less energy loss than a big, huge electromagnetic field. The other thing we've learned is the big, huge electromagnetic fields, organic life doesn't do well being constantly subjected to electromagnetic radiation. We've closely tied a whole variety of cancers to substantial exposure to electromagnetic radiation. Don't buy the house under the big power wire. Okay? Just don't go there. If you already own one, move. Rent. Rent it to someone else. Well, the truth is, the big high-powered ones, they're actually, well, relative to the currents we typically deal with, it's still pretty high current, but very, very, very high voltage. The other thing is, it turns out that if you transmit energy at really high voltage and fairly low current, well, it's even true in lower settings, but it turns out that electricity doesn't like running through the center of the wire. If it runs through the center of the wire, the current creates a bunch of eddy currents, and those eddy currents tend to interfere with the flow. So that it's sort of an impedance to the flow of electricity. So that has a tendency to go out to the outer surface of the conductor. Well, so those big high power transmission wires that we have, they're actually not wires. They're tubes. What we do is we take and make a sort of segmented, a segmented section where each one is segmented like this, all the way around, and each one of those segments are just long bands, and then we twist it, which is what locks them together. Okay? It's completely hollow in the middle. Then we kick it up to 90,000 volts or 67,000 volts or whatever it is. And as long as it's AC, when we get into transformers, we'll get the other fact more, we'll find out that I can swap current for voltage anytime I want. Okay, one way or the other. As long as it's AC, it's real easy. A very small amount of efficiency loss because the transformer does stay a little bit warm. You guys reach out and feel the hockey puck for your computer. It's a transformer kicking it from 110 down to 12 or 19 volts. If you feel the hockey puck, you'll see it's a little bit warm. Not much, but there's some loss. Okay. So more frequency is bad with respect to long power line transmissions. Fortunately, there are ways to counter it. Now, in the world of DC, will we do some kind of sneaky things? However, we do it because of a dependency on, remember I talked about the galvanic relationship between two dissimilar metals? No matter what I do, I'm going to get about, any cell is going to be anywhere from about 1.5 volts to about 3 volts, somewhere in there. The better top-end lithium ions might be 3.4 or 3.5. The cheap alkaline bottom-end batteries are going to be about 1.5. Lead acid, about 2.1 volts. So we figured out initially, put 3 of them together, you get a nice 6-volt battery. Well, actually, it's a little bit more than 6 volts, but that's okay. 6 is good. And if we stick 2 of those together, we'll get 12 volts. Well, we figured out the 6-volt battery, kind of the lights are a little bit dim. Okay, the lights are a little bit dim. The starter motor is kind of wah, wah, wah. Well, that didn't work, particularly as you moved past World War II, and everybody needed a little bit more power. Okay, they needed to be cruising, getting into the era of the muscle cars. Okay, the big high compression engine. Well, the little 6-volt battery couldn't start the engine. Just couldn't get the motor starter motor to drive it. So we fairly quickly went to 12 volts. Well, we've already talked about what happens to voltage over a long distance. As we started getting into larger vehicles, where you had to have the battery here and the starter way, way over there, these big long runs of wire, it turned out 12 volts wasn't going to work. Because over that big long run, by the time you get to the starter at 400 amps, the starter's still only seeing 6 volts. Okay? So over those longer runs, we're going to need to run at 24 volts. Of course, if you take 12 cells at 2.13 volts per cell, fully charged, everybody's happy, you're really not at 24 volts. You're actually kind of closer to 28 volts. So as you see, I'm starting to build a pattern that voltage is a very, very loose target. Okay, we call a thing 12 volts, and it's actually a little bit more. And its charging is actually going to be even a little bit more. Just like what we say coming out of the wall, we might say it's 120, we might say it's 115, we might say it's 110. There are reasons why each one of those are valid values. Okay. All of it's approximate. So at the end of the day, this aircraft power, electricity, is going to have to come from some power device, some electromechanical generator. We often just bolt it onto the engine somewhere. However, in bigger vehicles, this is going to be primarily airliners or airplanes, big airplanes, and boats and ships. Typically don't see an auxiliary power unit, auxiliary power engine on cars or trucks or those types of devices. Boats and ships very, very commonly have an auxiliary power unit, usually runs off the same fuel that the main engines do. And in fact, what's happened to boats, which I think will ultimately happen to airplanes, is they got rid of the main engines. Threw them overboard, didn't need them. Totally a waste of time. Man, this big engine's there, big shaft, big screw, all this stuff. Drive the boat around and you can't steer it for squat diddly. Okay? They figured out, wait a minute, let's just put these big electric motors underneath the hull, and we'll put it on a big pivot so the electric motor can twirl around any which way we want it to go. In fact, we'll put several of these and some bow thrusters and a few other things. Okay? Then we'll just take and put in about 10 auxiliary power units, or 6 or 8 big, huge engines driving generators. Okay, each one of the electric motors 14 megawatts. Okay, that's about twice what all of Mira Mesa needs to run right now. That's each one of those electric motors. Okay, well here's the rub. If they've got 6 of those APUs running, 4 of them cause the boat to go full blast. 2 of them run all the light bulbs on the boat, on a cruise ship. They got a lot of light bulbs on a cruise ship. A whole lot of other stuff running. So, but it turns out they went completely electric. Their generators now operate at a very constant fixed RPM, the most possible efficient RPM for the ventilation, timing, everything that's been done with that engine, producing electricity, and they can just turn the fuel down, turn it up, turn it off completely if they don't need it for that particular engine. The power units that sit underneath the boat, okay, they've got a boat kind of shaped right there. The guy's got a little Windows computer screen. He takes his little mouse and I got it off. He takes his little mouse and a little cursor thing, and so he's got the boat like this, and it kind of comes like this. And he's got it there, and all the engines are there, and he's got this little thing. He takes his little cursor and he drags this thing over here. And okay. Goes over here, picks some button like that, goes click. All the electric motors move around, and the boat goes and pivots right around that spot. If he needs the boat to shift a little bit because there's a dock right there, he can give it a shift to here and then a second spot to there. So as it moves, it'll go like this and end up right there. Stop. Okay, you just limited in need for any tugboat or anything else. It's cool technology, right? Well, we're not there with airplanes yet. My guess is we're not that far away. We're really not that far away. What's happened in the world of small vehicles, air vehicles? Don't they all have 4 little electric motors or 6 little electric motors or a dozen little electric motors? And they're all working in coordination with automated computer systems. Okay, we just need to make the battery a little bit bigger and put a seat on it. Okay, we've already got the motorcycle seat. I assure you I can find a motorcycle seat, I'll bolt to it. Yeah, baby, let's go. Right?
Mhm.
We're right about there. So that, and by the way, this technology, this has already been around for 20 years on the big ships. They're called Azipod motor drives. They've been around for a long time already. Um,
So you're saying they don't have a big prop and a big.
they do have a big propeller, but the propeller is designed, now the propeller is designed to operate at a very, very specific RPM for maximum efficiency. The other thing that's really cool about it is you've got this pod that comes down with an electric motor like this, like that, and a big propeller, right?
Mhm.
The propeller doesn't thrust this way. It thrusts this way. Okay? That way, this pod fills the cavitation void, so they never cavitate.
Hmm.
And it gets cooled. Now, I don't know what it takes to rotate this thing around while 14 megawatts are being driven through it. Those must be some bodacious brushes up there. But and again, this is not new technology. It's been around a long time already. Almost all, if not all, cruise ships now use this technology. Many of our freighters and tankers are using it. Okay, meanwhile, back in the world of airplanes, well, we did a couple of things early on. One of the things we did is we just took a fan, kind of like this, and stuck it on a generator and hung it out in the breeze. In fact, we got sort of clever about this. We said, look, you can buy your airplane with or without electricity. We'll put it in the type certificate. If you buy it with electricity, its gross weight's just a little bit higher. You put these parts on, it's great. If you buy it without electricity, which most people did because they didn't have radios, they barely had radios. Only a few airports had the radios installed. So most people didn't. Well, that sort of affected us down the road when we came up with this whole new category of certification called light sport. And what the FAA did is they said, you know, there's all these little airplanes out there that if they had electricity on them, they weighed a little over 1,320 pounds. If they never had electricity on them, they weigh a little less than 1,320 pounds. So we're going to make that the number for light sport airplanes. If it's ever had an electrical system on it, which even though it's in the type certificate, you would have had to told the FAA, then it doesn't qualify for light sport. Because they were trying to limit the number of airplanes that fell into this new category that's now, 15 years old. I think at some point they'll probably broaden that just a little bit to include some more airplanes in there. But these things are still fairly commonly in use. In fact, the only time I've had to repair one of these was a buddy of mine in his Taylorcraft has one of those. He flew into Oshkosh one day. Said, God, I was flying over Iowa, and all of a sudden that little generator took off and started vibrating and doing all kinds of weird stuff. So I had to land and tie it off. So he had it tied off. He said, I think one of the screws came off and it put a big ding in the blade, and that caused it to be out of balance. Well, I started looking at it, looking at the ding. It wasn't a ding, it was a hole clean through the blade. And it had a nice splash, and I'm looking at it. I start turning the blade around, and I'm turning the blade around, and turning the blade around. Finally, I find a spot where that hole lines up with a nice gouge along one of the lift struts, with one of the lift struts here below, went right through the fabric of the gear leg right there, right up through there, caught the second lift strut, made a nice little gouge on it, and then right up through the wing. Somebody shot him. I was like, Charlie, somebody shot you. No way. Yeah, somebody shot you. You need to, of course, one of our buddies that had a security there, he's like, yeah, we got to call the police. And a whole lot of people got involved. TSA and everybody else. You don't shoot at airplanes. Yeah, that was kind of scary. Anyways, another one, a little bit more fancy. And they actually have ones that are really, really fancy on most airliners. It either flops out and sticks out in the wind, or a door opens. We commonly call them a RAT, or ram air turbine. Okay. Works like a champ. Just blow a bunch of air across the fan. It's no different than those big wind generators you see mounted all over what is it, Banning Pass or, out here off of Interstate 8. It's just a lot smaller. Okay. Another thing we could use an electromechanical generator for that's kind of cool is we could use it as a signal generator. Okay, so imagine there you are, you've just designed your first B-29 bomber. And you've got 4 big Wright 4360s hanging on it. And the distance from the instrument panel, we'll give you a little bit. Go to the flight engineer panel, right? No, it's got to be on the instrument panel. All the way back to the center of the airplane, all the way out to the wing, all the way forward back to the back of the engine for the tachometer output. Okay, we're going to have to run a cable that whole distance. A mechanical cable going flop, 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 flop. I don't know, 400 feet long, right? Flopping all over the place. It's not going to work. No way are you going to get a cable that long to be able to draw it. So you got to do something to make the tachometer work. Well, it turns out if I make and use a small little permanent magnet with a 3-phase generator, and I start generating current, and then take the wire coming, electricity coming off of those 3 phases through 3 wires to a 3-phase AC motor with a permanent magnet in it, not only will this magnet spin at the same RPM that this magnet will, but they'll actually stay in phase with each other. Okay, they will follow each other exactly. Now all I have to do is run 3 little bitty wires the whole length. And not only can I run my tachometer off of this, but I then can also run another device off of here and use it to synchrophase both of or all 4 engines, to get all 4 engines in phase, so that the propellers not only are at the same speed, but that the propellers travel at the exact same path. Okay, that's particularly important, particularly when they're doing this, because you want to reduce the amount of pulsing and beating. You guys ever been on a boat or in a twin airplane where it's kind of going wow, 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 wow? You start getting it dialed in, wow, 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 and kind of get it dialed. At 4 engines, you can't do that. Not without some kind of more advanced technology. Well, so that's one type of electromagnetic generator. Another one, which many of you may have in your cars, electromagnetic generator. Kind of simple. What we do here is we're going to take inside there, and there's a couple of ways of doing this, but we'll use what they're doing. We got 3 wires. A 12-volt signal comes in. A big coil comes out like that. Okay, positive, negative. Then we're going to take a second coil off of here, like this, and that's our signal, right? This electricity is going to create a magnetic field around a coil, or around a permeable element in here, right? So I'm now going to get some big magnetic lines of flux forming here when that electromagnetic magnet's on. I'm then going to take my piece of steel or iron and I'm going to go whoosh right by there. When I do, this magnetic field's going to go whoop, 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 real quickly. And when it does, it's going to cut across this inner coil. And so when I look at the voltage on that, I look at a voltage line, as the magnetic field, or as the steel goes by, it's going to go whoosh, whoosh, like that. And they actually ripple a couple of times in there. Okay? If I feed that data to a computer, the computer says, okay, anytime the voltage goes above a certain point, when it snaps back down to right there, below that threshold, I'm going to say, that's the point in time that matters. Now, what is this wheel connected to? Maybe it's connected to your crankshaft and it's telling it where number 1 cylinder is. Okay? Or maybe it's just counting the speed and it's telling you what the speed of the crankshaft is. Or maybe it's connected to each one is connected to your wheels. And it's telling the computer how fast your wheels are spinning. And when you slam on the binders and one of the wheels starts skidding and starts slowing down rapidly, it says, oh, we got one of the wheels slowing down. We'll start anti-skid pulsing the brake. Okay? So we now use an electromagnetic generator as a sensor. Not a lot of current, we don't care, all we care about is the data. Any moving parts?
Just the wheel.
Well, the wheel is part of the crankshaft,
Okay. That does.
or part of the wheel, or whatever, right? You know, in here, there's no moving parts. Theoretically, should never wear out.
Yeah.
Well, we can't have that, right? So we're gonna have to somehow make the wire cheap or do something. Okay, gotta have it break at some point in time. Well, theoretically, we don't do that in airplanes. So yeah, wheel speed sensor, crankshaft speed sensor. You could theoretically have, you know, a steel piece and a flap actuator, or you know, some other control that tells you when that thing goes whizzing by, that it, you know, physical motion has occurred. So electromechanical generators are often used in other venues where the purpose is data, not necessarily a power source. Tell you what, let's take a break here. Go out and do your battery. Yeah, take about a 15-minute break. Go out and do your battery. Then we'll dive back in and do one more battery thing and be done for the evening.